In this section, I'll briefly introduce some of these problems that you've seen and used before, but just so that they're given with some specific notation that we can refer to. I hope I've been consistent whenever I use them. So dominating set is you're given a graph and you cover all the vertices by picking vertices, a subset of vertices, so that every vertex is either picked or one of its neighbors is picked. A Hamiltonian cycle means a path in a vertex that visits every vertex exactly once. So there's two versions, directed and undirected, given depending on whether the graph has direction on the edges. These are all part of the classic problems that you worked on, or some of you worked on. Clique is, can you find in a graph a complete subgraph of a certain size where all possible edges are there? An independent set is the opposite. Can you find an empty subgraph of a certain size? Then we had the traveling salesperson problem, which appeared earlier on, so I don't want to repeat the definition. We'll come back to that in the next chapter. And then graph coloring is it's a problem where, again, given some graph, and we have to assign colors to the vertices so that none of the edges have the same color on the two endpoints. And the question is, can we do this with a certain number of colors? Set cover is a problem that will come back to us at some point later. We're given subsets of a universe, and we try to cover the entire universe. We have to pick subsets so that all elements are covered. And the question is, can we find a small enough selection? There's a weighted version where the sets have specific costs, and then the question is, can you do it with a bound on the cost? This is actually a general theme that you will see in many problems. There's often a combinatorial version where the cost is just a number of things, and then there's a weighted version where the cost is the sum of the costs of the elements you select. And oftentimes, the two are very similar. It's often the case that both are hard or both are easy. I mean, one example where both are easy is shortest paths in graphs. If you have a graph that's unweighted, then this is just breadth first search, and you find the shortest paths by number of edges. And if the edges have weights, then you know algorithms for that as well. Either Dijkstra's algorithm if the edges are non-negative, or Bellman-Ford. Then you can find the shortest paths by the sum of edge weights. Right, in this case, both problems are in P. They're efficiently solvable. A problem that's a bit different from the others we've previously seen is this one, closest string. Here we're given a collection of strings of the same length. And the question is, can you find some other string that has Hamming distance at most k to each of those strings? And Hamming distance just means how many characters are different. So you count how many mismatches you have. And that's also a hard problem. We might come back to this at some later point. Max cat is, again, in a graph. Can you distribute the vertices into two sides, a left and a right, or a set S and T, so that the number of edges that go across the cut have one endpoint in one set and the other in the other set is maximized, or is above a certain threshold. And we know that the converse problem, minimum cut, is a problem in P. It's efficiently solvable. That's the famous max flow min cut that you may have seen in algorithms classes. But if you flip around the problem and you ask for a cut with many edges across the cut, it's a hard problem. And last one is, again, famous cut problem, exact cover. It's similar to set cover. You have subsets of some universe, and you want to cover all of the elements in the universe, but this time you're supposed to cover each element only once. So the sets have to be disjoint as well. Any questions on those problems? Many will be familiar, like you've had those before. As I said, I just wanted to have a canonical definition that we can refer to if we use those problems or those names. Of course, there's many more problems and many more NP-hard problems. In particular, this book on computers and intractability, Gary Johnson, has hundreds of problems that are known to be NP-hard, or NP-complete in many cases. I think all those problems are NP-complete. But we don't need all those problems here. Yeah.
How is Hamiltonian cycle different from traveling salesman?
Yeah. So the traveling salesperson problem, I didn't go over the definition properly, but we'll actually need it in the next section, so maybe it's good to revisit. Here the input is a complete graph, but it has weights on the edges. So in a way, you could say TSP is a weighted version of the Hamiltonian path problem, where the Hamiltonian path has a graph without weights. There's either an edge or not an edge between two vertices, and you're trying to find some round trip, but you can only use existing edges. And TSP, all the edges are in principle there, although you could put the cost of an edge so high that it's effectively not usable anywhere. But in principle, all the connections are there, but they have different costs, and so the question is to find the shortest round trip, or one that's below a threshold. Yeah, that was a good question. But the problems still feel very similar, right? They're closely related. This will come back actually. Okay. Other questions about the problems? There's a few more that have a slightly more numerical flavor. Subset sum is given a list of integers and asks if there is a selection of those that sum to exactly 0. So here these are positive or negative. You can, I guess we technically haven't defined for our Turing machines how we deal with negative numbers, but I guess you can imagine there's a minus in front and you have to adjust how the arithmetic works. You could also formulate the problem with giving a specific value that you're trying to match. But this, I found this one surprising when I first learned about it. So just a collection of numbers, why should it be hard to find some subset that sums to a certain value? But it's also a hard problem. You can do reductions. The knapsack problem, we'll see later again, is given a collection of items. So these items 1 up to n, they have a weight and they have a value, and you're trying to fit as much value in your knapsack, but you can't exceed the weight bound. So the collection of items that you select has to sum in weight to at most a certain threshold, and you're trying to achieve at least value k. Bin packing is also given items, but here we only have weights and some capacity for bins, and we're trying to put the items into as few bins as possible. So here the way I formalized it here is you assign the elements to 1 out of k bins, and then in each bin you have to sum to at most the capacity. For most of these problems, there's an optimization version and the decision version. We'll come back to that. And the last one, this might also be a good question. This will come back in many cases. Who has done some course on linear programs and linear optimization? LPs and ILPs. Has anyone seen that ish? Okay, then maybe it's worth spending some time on this in another chapter. It's a beautiful piece of theory or applied mathematics, or I don't know what you want to call it. It's often done as part of operations research, so more business-oriented studies often do a little bit of that. because it's a standard tool that you can use to optimize business processes, production, and so on. But it's also a great algorithmic tool. Okay, so I'll plan a little bit on that. For this problem, maybe this sounds a bit weird then for you, but the definition, I guess, is easy. You're given some matrices or vectors of numbers, this matrix A and a vector B and another vector C and some threshold. And the question is, can you find a vector of zeros and ones? So that here, this is a matrix vector product. Standard linear algebra comes haunting us again. So you multiply this vector on the matrix and you get back a vector. And so this less or equal is intended to be element-wise less or equal. Right? The first entry of the vector should be smaller, second, and so on. So this is essentially a system of linear inequalities. That's what that says. So you're trying to find some vector x that satisfies a system of linear inequalities and has a dot product with this other vector c that's above a threshold. So the theory of linear optimization, these are side conditions, maybe capacities of some machines that you cannot exceed. And this is somehow the gain or the reward you get, your profit. And X is some way you can have a decision, do it here or do it there. We'll come back to this then. Okay. Well, as an abstract question, this is also an NP-hard problem if you're trying to find these 0, 1 vectors that satisfy these inequalities. Okay, that should be all. Questions on the second set of problems, more integer-related ones.